Here's a puzzle. Why does a strong base ignore alkanes and alkenes, but easily pulls a proton from a terminal alkyne? That surprising difference is the key to powerful carbon-carbon bond building. In this video, you'll learn why terminal alkynes are more acidic than alkenes and alkanes, how to form the acetylide anion, and how that anion creates new carbon-carbon bonds through SN2 substitution and carbonyl addition. So, why are terminal alkynes more acidic? The answer lies in orbital hybridization. The more S character an orbital has, the stronger its acidity. An sp3 carbon has 25% S character, sp2 has 33%, and sp has 50%. An sp-hybridized carbon holds negative charge closer to the nucleus, which stabilizes the conjugate base. As a result, terminal alkynes are the most acidic of the three. To put numbers on it, on the pKa scale, alkanes are around 50, alkenes about 44, and terminal alkynes near 25. That's a dramatic difference. Still weak acids, but acidic enough to react with strong bases. Now, how do we deprotonate a terminal alkyne? For this, we need a very strong base. One option is sodium amide, which removes the proton to give the acetylide anion a carbon with a negative charge, along with ammonia. Another option is sodium hydride, which produces hydrogen gas. And finally, N-butyl lithium can also do the job. Once formed, the acetylide anion has unique reactivity. Because it is linear, highly basic, and its negative charge sits on carbon, it acts as an excellent SN2 nucleophile. This brings us to our first application, substitution. In SN2 reactions, the acetylide anion attacks a primary alkyl halide, like bromoethane, from the backside. Bromide leaves, and the result is a larger internal alkyne. But here's a limitation. Avoid secondary or tertiary halides. With those, the acetylide is too bulky and strong, so E2 elimination dominates instead of substitution. That's why primary halides are the best choice for clean SN2 reactions. Curious how much you're remembering? Your personalized practice test, flashcard set, and study guide are all waiting for you. Just tap the link now and keep watching. Future you will thank you. The second major application is addition to carbonyl compounds. When the acetylide attacks the carbonyl carbon of an aldehyde or ketone, it forms an alkoxide intermediate. After workup with water or dilute acid, this intermediate becomes a propargyl alcohol. For instance, adding to propanal gives RC triple bond C, bonded to a carbon bearing a hydrogen and a hydroxyl group, followed by CH2 and CH3. Which alcohol you get depends on the carbonyl. Formaldehyde gives a primary propargyl alcohol. Aldehydes give secondary, and ketones give tertiary. Same mechanism, different substitution outcome. It's crucial not to skip the workup. Without water or acid to protonate the alkoxide, you won't see the alcohol at all. And remember, this chemistry only works with terminal alkynes. Internal alkynes lack an acidic proton on the sp carbon, so they don't deprotonate under these conditions. To recap, use strong bases like sodium amide, sodium hydride, or N-butyl lithium to form acetylides. Couple them by SN2 with primary alkyl halides, or add them to aldehydes and ketones, followed by water or hydronium workup. And here's the big picture. Terminal alkynes are reactive because their higher S character makes them more acidic. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet, content made just for you.